right, so those of you who already took some AP Science principles, this might be too easy. Sorry. Oh, I also know that engineers take this as well. You know binary numbers?
Yeah, I took digital electronics.
Yeah, that's where you learn it, right, yeah. Okay, so this will be a review. So here's a question. What if we didn't have 2, 3, 4 through 9, but only 0 and 1s? You probably heard it from somewhere, or you already know that computer records numbers in its memory as 0s and 1s. Now, this won't be a problem when you have to record 0 or 1. You can write 0 as 0, 1 as 1, so there's no problem. Okay? But now, if you try to record the number 2, how do you record that? And the way you do it is by using 1 and 0. So use 1, 0 to stand for 2. Now, for some people, this might feel uneasy because you might think, well, then, if I'm using 10 for 2, then what do I use to represent 10? Well, it just goes up. 10 actually will become what? 1, 0, 1, 0. Yeah. 1, 0, 1, 0 will be 10. Okay. So, is that right? Yeah, 1, 0, 1, 0. Okay. Now, this is really confusing, so we'll put 2 mark under it, and this is what's called binary number system. It's a way to represent numbers by just using 1s and 0s. Okay. All right. So here's an example. I just wrote this in the previous lecture, but you can continue to add 1 to get the next number. So if I want 3, what do? I said 1, 0 is 2, right? So you add 1, 0 plus 1, that gives you 1, 1, which is 3. Right? And then if you do 1, 1 plus 1, now let's think about what happens when you do 1, 1 plus 1. That's important. 1, 1 plus 1, 1 and 1 will be added, so you might say this is 12, but that's illegal because 2 is not allowed. So instead of writing 2, you have to use 1, 0. So it'll be like 1, 1 plus 1. Maybe I should right here. Okay. Let me write over this. So if you have 1, 1 plus 1, 1. 1 plus 1 is 1, 0. So you put 0 and put a carryover as 1. Okay? Because 1 plus 1 is 2, but 2 is represented as 1, 0. And now you do another 1 plus 1 here. But 1 plus 1 is again 1, 0, and there's another 1, so it's 1, 1. Oh. That's not what this was trying to do, sorry. This will be 3 plus 3, okay? 1, 1 is 3, so this will be 3 plus 3, so we know that this result is 6. So 1, 1, 0 will be same as 6, okay? Yeah, I was trying to do really 1, 1 plus 1, so if you do 1, 1 plus 1, then 1 plus 1 will give you 0. There will be a carryover, and 1 plus 1 will give you a 0, and then there will be a carryover. So there will be an additional 1 here, so you get 1, 0, 0. That's why you get 4. And then you can keep adding 1. Okay? So a good exercise is to try to do 1, 0, 1 plus 1, which will give you 6. 5 plus 1 is 6. And I did it here. It's 1, 1, 0. Any questions so far? Is this good? No? All right. So I want to show you how to count to 1,000 using just your hands. Okay. So think of it this way. let's say you're trying to count people passing under the bridge. Okay, that you want to see, or maybe how many cars are passing under the bridge in 1 hour. Okay, and the thing is, the easiest device for this will be a clicker. Just click, click, click. You know how people do that in front of a theater just to see how many people went in. So they would do click, click, click. The second best thing would be having a pen and pencil where you mark every ones, right? And then every fives you do a slice and then you get to the next one. But let's say you don't have any of those. Then up to 1,000, you can just use your hands, and just by mimicking your binary number. So it's like this. You have 1, okay? So let me do it this way, okay? So 1, and then what you do is 2. You don't do 2, but you do 2. Is this okay? So 1, 2, right? And then 3 would be 3. Are you getting this? This is 3. Right?
Were your fingers down ones or zeros?
So down is 1.
Down is 1.
Up is 0. Okay, so if I do 1, that's 1. If you do this, that's like 1, 0. Right? 1, 0, which is 2. Right? And this will be 3. Now guess the next number. Can you show it to me? What's the next number? This. Right? 4, right? 5, 6, 7, right? 8, 9, 10, 11, right? Just a minute. That's 8. Right, 8, that's 11, and then 12, 13, 14, 15, right? Okay, so you can actually train your fingers to do this in real time. It's not that hard. So if you do that, that allows you to count up till 1, 1, 1, 1, 1, 10 ones, right? 10 ones is 1 less than 11, 1 and 10 zeros. That's 2 to the 11th power, which is 2048 minus 1, 2047. Is that right? No, that doesn't make sense. Okay. It will be 2 to the 10th power, 1024 minus 1023. So you can represent numbers between 0 through 1023 by doing this. Okay? You can count up to 1000 by using your hands, okay? Using this binary number system. It's a different way of representing numbers. Okay? Hopefully that gave you some sense of what binary numbers are. There's a quick way to convert between a binary number and a usual decimal number. If you see 0, 1, 0, 0, 0, 1, 1, 1, binary, then this last digit will be the ones digit, the next will be 2, and then that's 4, 8, and we're going by powers of 2. So this will be 2 to the 4th power, 16 to the 5th power is 32, 2 to the 6th power is 64, 2 to the 7th power is 128. So you can convert this by just saying it's 1 times 64, 1 times 4, 1 times 2, 1 times 1, and that gives you 71. So this represents 71. Okay. All right, so I asked everyone to bring a computer. So I have Python here, but now if you don't have Python installed, what you can do, type in online Python. And if you do that, there's the something like this. And let me show you how this one works. So 0B111 converts binary number into a decimal number, and then bin of some decimal number converts it to a binary number. Okay, so let me show you how this is done here. If I do print 0b 010011, and then if we execute that, it gives you 19. And that's because this is 1, that's 2, 1 plus 2 is 3, and this is a 4th digit, 8th digit, and this is 16th digit. So this one represents 16, 16 plus 3 gives you 19, so that's why it gives you 19. Now to convert this 19 back into the binary, you can do print binary of 19. Then if I run this, both lines will be executed, and these are what you get. You can see them converting back. All right, so after today's class, I want everyone to install Python on their laptops. I already gave you the link by going to Anaconda Download. Some of you who already took the computer science course, a computer programming class, probably have this on your laptop. So make sure that you have that loaded up. And if you have installed the Anaconda Download, then there are two things that we will be using a lot from the Anaconda distribution. One is Spider. So if you're using Windows, you can type here. Once you install it, you can type Spider, and then you can run that and get this program. And another one will be something called Jupyter. But this one, I'll explain it later in the class. Okay. So if you execute Spider, the nice thing is on one side it has the execution, the coding panel. You can write commands and run to execute everything. On the other side, this is called the console. In the console, you just type anything and it gets executed right away. So if I do the same thing I did over there on the online Python version, say 0b010011, it will give you 19 right away. And notice that I didn't even have to put the print one. Any value will be valued, and that value will be returned. And I can also do bin of 19. Same thing as before, or just bin of 19. If I do bin of 19 on this side, it doesn't do anything because the values are not captured in the console. You will have to print it to see the value on this left side, just like how I did it in the online one. But if you're on the console, you just have to do, you can do just bin 19 and it gives you back the binary. Okay, so let's continue on. Now let's talk about bits and bytes. When you try to buy a new laptop on some online market, a lot of times you'll see that the computer has 8 gigabytes of RAM or 16 gigabytes of RAM. What does that mean? Well, byte is 8 bits, where each bit can represent either 0 or 1. Okay. When you buy a memory module, how many of you have built a computer? You built a computer. That's good. Yeah. All right. So you bought RAM sticks and put it there, right? Okay. So those memory modules, they store information in 8-bit packages, which are called bytes. So 1 byte is 8 bits, and a byte can store from 000000000 to 11111111, and this highest value here will be 255, which is 2 to the 8th power minus 1. Okay, and then you can think about how many gigabytes of RAM you have on your computer. Okay. Now there is some talk about what this means. So there's a difference between gigabytes, the usual thing that people use for measuring memory and memory stick, and gigabytes, GI bytes. And the difference is if you say 1 gigabyte, well, 1 gigabyte is equal to, well, first of all, 1 kilobyte is equal to 1024 bytes. The reason for that is because 1024 is 2 to the 10th power. So that's how people measure it. But that goes against the standard convention of kilo being 1000. So there's another way people say this. It will be 1 ki byte, kilobyte. If people write like this, then that's 1000 bytes. So there's a difference between these two systems. So when you say 1 gigabyte, 1 gigabyte is kilo is 1024 times bytes, and mega is the next one. Mega is another times 1024, and then on the next one is giga. Okay, so it's this much. That's 1 gigabyte. Okay? So you can see that 1 gigabyte, what this tells us is that 1 gigabyte is really same as 1.07 gigabytes. So there's a slight discrepancy, and this becomes larger and larger as you go up. Now, at some point, hard drive manufacturers like to blow up their numbers, so they were using the other standard rather than the usual gigabytes. So when you read hard drive, you have to recognize these as really like this one. So I just wanted to point out that discrepancy. When we talk about gigabytes, there are actually two types of gigabytes, and it's written differently. All right. Okay, now let's talk about hexadecimal number system. So this is like the opposite. Instead of having just 0 and 1s, now we add to 0 through 9 extra new numbers A, B, C, D, E, and F. So, for example, B stands for 11, C stands for 12, F stands for 15. Okay? So if you do that, then you get a number system that uses 16 different numbers rather than 10. So it's called hexadecimal number system. Hexa means 6, dec means 10, so hexadecimal means 16 system. And then in Python, hexadecimal numbers are denoted by putting 0x in front. So if I do 0x B, that's going to be 11. And then 0x F, that'll be 15. Okay. But that's the last number. How would you represent one more than F? 1 more than F would be? Well, that number will be 16, but how do you represent that in hexadecimals? If you run out of the number, what do you use? 1, 0. Yeah, so you use placeholders to get the next number. Okay? This was the great invention of the Arabics, right? So Arabs, they realized that, see, Romans, they thought they had to invent new letters for any new number. So they had the X for 10 and then C for 100 and so on. But then Arabs realized you don't have to do that. You can just use place values to hold numbers. And so they used 10 for 10. But then in hexadecimals, 10 would be 1 more than the F, which is 16. So that's how you get that. Okay. And then to go the backwards, you have to do print hexadecimal version of 16, and you get 0x10. Okay. That's how I do things in Python. Now, why are hexadecimals nice? Well, that's because let me try to explain it this way. So if you have the hex of the binary 1111, you get 0xf. That's because 1111 is 15. But then if you do hex of 1111 and you add 4 more zeros, it gives you 0xf0. And then another 4 more zeros, you get f00. In other words, every 4 bits can be converted into 1 hexadecimal digit. And because you can just truncate a very long binary into 4 bits and just convert them separately. So for example, let's see, if I have 1011, that's B. And what about 1001? That's going to be 9, right? So if I need to convert 0b, the binary of, say, 1111, 1011, and 1001, then this 12-digit binary can be truncated into 4 bits, and you can convert them separately. So the first 4 binary is 1111, that converts into F, as we've seen before, right here. And then the next 4 bits, 1011, gets converted into B, like this, right? And then 1001 gets converted as 9. So that's how these get converted, okay? So I will be putting these type of questions on the exam, so you should try to teach yourself how to convert binaries back and forth and also hexadecimals back and forth. Okay, now that immediately tells you how integers are stored in the computer. After all, this course is Intro to Data Science, so one of the questions that you should have is like, if you get numbers from data in the real world, how do they get stored in the computer, right? That's the reason we're doing this in the data science course. And my first answer is, at least for integer values, what we are doing is we can convert them into binaries and I can store them. Okay? If I use 1 byte, then the maximum number I can represent is 255. If I use 2 bytes, 2 bytes will be, what, 2 to the 16 different numbers. So the highest number you can represent is 2 to the 16 minus 1, which is 65,535. That's the highest number. And now you use more bytes, then you can represent bigger numbers. Now, normally in C++ or Python, you represent numbers using the using 4 bytes or 8 bytes, and the leading bit is used to represent plus or minus. So that tells you that when you have an integer thing, you might have you have numbers that can't be you have numbers that are too big to be stored in those bytes. Okay, and that's where you can cause bugs, and that's how overflows happen. If you have wondered how hackers hack into your computer system, they look at various ways that your computer program can break. Okay? It tries to use do different things. Right, so there's a joke where a company made a software about ordering beer in a bar, and the UI tester, the software tester tested all these edge cases, like comes in and orders 0 beer, comes in, orders 10 beers, or comes in, orders like 1 trillion beers, and does all kinds of different things, right? And none of the problems happened. All these problematic points were addressed in the software. So the tester said, okay, this is fine. Let's deploy. And the first customer that walks into the bar asks, oh, how do you get to the train station? So the joke is that the tester, when people write programs, they think they can, they filled in all the possibilities, but when it's deployed in the real world, there are always cases where the software is not ready to respond in the proper way, and you end up the software breaking, and sometimes you can make it to break to be in a vulnerable state where it could run other codes at different locations, stuff like that. So like anytime a software is made, there's always a way to, like, some holes. So there was one time where, like, in C++, a very simple print hello world. Like, how simple can it be, right? That had a 0-day flow. You could hack a computer which ran that software. So that's always an issue. People don't look under the hood how things are implemented, but being able to know how things are implemented gives you a deeper understanding of what goes on. I mean, at least by knowing that computers use bytes to store things, and in C++ people use either 4 bytes or 8 bytes for short integer, I think, uses 4, and then long integer uses 8 bytes. So that tells you that there's an upper limit to the integers. And if you're writing programs that takes in any 2 numbers and you reply by adding 2 numbers, that could be a dangerous kind of question, right? That software, it doesn't know how to handle numbers that are too big, right? So, that's one thing, one reason why you want to know this. But additionally, you might benefit from this by knowing how many bytes is needed to store a number. So think about the following. Your company is running a big data, right? And if you're using too much memory, then it's hard to store it. It uses more disk space, and the bigger the system is, it could be faulty. So the higher ups in your manager says, okay, we need to know how to reduce this data. Okay? Now they look at the zip code. Well, zip code is 5 digits, and let's say they're thinking of each digit as a letter, which uses this ASCII character type of encoding, and each letter takes up 1 character, which is 1 byte. Right? So it uses 5 bytes for all the zip code. Right? Yeah, 5 bytes. But then, see, a zip code is between 0, it's a number. It's definitely less than 2 bytes. It's more than 255, so you can't do that, but it's less than 2 bytes. So you can say, okay, we can save some memory by, instead of using 5 characters for storing the zip code, let's just use 2 bytes integer. So it'll be either short integer or short integer in C++. If you do that, then suddenly you've saved, what, 60% of the data space for storing zip code. Okay? That could translate to a lot of things. Right? So these are the things that you can think about. It also gives you some idea of how large your database should be, looking at the type of data. So those will be another topic that we'll visit in the next class. But let me just first talk about this. For today, we'll finish at somewhere here probably. Okay, so a few more slides. So we talked about how to store integers, but then you might ask, like, how do we store characters? Well, so the characters, like A, is stored in your memory as number 65, or in terms of binary, it's 101. So let me show it on the computer. So if I do print order of A, it gives you 65. So 65 is the number for that is stored to store letter A. Okay, that's called the ASCII code. Now, in the early days, when computers really had to save memory, they were using just 7 bits. Where is it? They were using just 7 bits for ASCII code. And let's see. You can see here that the capitals and lower cases are given different letters. So if I used lowercase a, it would have given us 97. All these numeric values, so 0 as a character will be number 48. So you have to know the difference between integer 0, which is encoded as 0, and 0 as a character, which is encoded as number 48. Yeah, it's number 48. Oh, I thought this is binary, but this next number is called octal. People don't use octal that much. It uses numbers from 0 through 8. So, I mean, this much was enough to represent all the letters that's used in the computer in the very early days of personal computers. Right? And if you're working with an Apple computer, Apple IIe or something, this was all they could store. So if you were a European and you needed to have some, what is those called? Like if you have AN with something on top. Do you know what those are called? So those special characters that French use, those will need higher numbers after 127. So those were available for the extended ASCII code. Yeah. So this means that a single information stored in a byte could be interpreted as a number in one context or a letter in another context. The way it's interpreted depends on the program, how the program uses it. Okay. But then, nowadays you have more than that, right? Koreans use computers, Chinese use the computers. So, this is the extension of ASCII to include these dialectic. I think it's called dialectic. So these extra markings on the top. So those are given additional numbers, and then there are additional encoding ways. So there's something called a Unicode, and I don't know what this one is. I've never seen this one, but there's the standard one that people use is UTF-8. So what UTF-8 does is it uses the regular ASCII for basic ones, basic letters, but then some letters will use 2 bytes. But then, Chinese characters, there are so many different Chinese characters. So for Chinese characters, sometimes they might use 3 bytes or 4 bytes. There are emoticons. You know what those are, right? Emoticons also use Unicode. So, for example, if you wanted to insert something in an email, so let's say you wanted to do, let's see, calculator Unicode. So if you do that, then there's a Unicode character for this thing here, right? Which you can just copy and paste it on your email as an emoticon, even if your typewriter doesn't, your keyboard doesn't have the emoticon thing, you can use this. And they have their Unicode number. Okay? And these are hexadecimals. A9 is hexadecimal, F5. So this is using 3 bytes to represent this. So a lot of the Unicodes will use 3 bytes. So that's how a computer stores extra characters as this. Now there's also another standard which is called UTF-32. UTF-16 is something in between, but UTF-32 is good because it will always use 4 bytes to represent any character. Now, some might say this is waste of memory because most characters only need 1. So when you're storing a text file, normally it's stored as UTF-8, but sometimes you might have to process this into your computer, and the code might be more efficient if it always uses 4 bytes. Okay? So in those cases, it uses UTF-32. Right? We're going to be working with some hex editors next time, and we can see in Python NumPy package, strings are usually stored. If the string "have a nice day" with the smiley face is encoded using UTF-32, how much memory would this need? Okay. And if you count this, there's no space after the period, and spaces do have it is 1 character, and dot is a character as well. So you can see that this is 17 characters. And because it's UTF-32, 32 means it's using 32 bits to encode 1 character. 32 divided by 8 gives you 4, so that means 4 bytes per character is used when you do UTF-32 encoding, and that gives you 68. Now, however, what if we use UTF-8? Well, in this case, for basic letters, how many bytes would it need? Like H. UTF-32, we just did that, 68. Yeah. I'm asking for, if you do UTF-8, how many characters, how many bytes for 1 character? H. Oh. My connection's bad. It's good now, right? No? Good? All right, okay. So let's go back. Now, the second question is, what if we use UTF-8? In that case, this regular character H, how many bytes would it be used? Would be used? Just 1, yeah. But for emoticons, how many? It would use 4 bytes. So the idea of UTF-8 is use less bytes for things that are used a lot, and you use more bytes if you're using something that doesn't get used a lot. Okay? So, so for some European letters, it may use, or Greek letters, it may use 2 bytes. Okay? And then for Chinese characters, usually the Chinese characters that are more often used use 3 bytes, and the ones that are less used are 4 bytes, but not always. And emoticons are 4 bytes. Okay, so we see that for 16 characters, it's 1 byte. So 16 times 1. But for that one character, this is 4 bytes. So what would that be? 20. So this would use a lot less memory, but because the number of bytes per character is not uniform, sometimes it's not desirable if you're trying to do some fast computation. So they have their trade-offs. Okay? All right, number 3, suppose a company uses 8-digit employee number for its employees. Okay. How much memory is needed to store the employee ID number, I'll say. ID numbers for 2,000 employees. So let's think about that. Well, the thing is, assume you are using either one of 1, 2, 4, or 8 byte integers. Okay. In C++, 1 byte integer, which can represent 0 through 255, those are called char character. And 4 would be just short int, and int would be 8. But it also depends on the CPU and the operating system. Different operating systems have some different standards of what long int and short int are. But let's say you're doing this. Okay? Of course, you can use length 8 string to store this, but that would be wasteful, and you are trying to be memory efficient. Okay, so with these conditions, let's think about how to go about it. So think of it like this. I have a hunch it should be 4 bytes. There are 4 times 32, no, 4 times 8, which is 32 bits. So the highest number it can represent is, well, that's going to be quite large, but let me try to write it, is 0b, meaning that this is a binary, okay? And I'm going to count 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That's the highest number. Now the problem is I need to know what this is in terms of decimals. Okay, so how do you know? Well, we just learned how binary systems work. This is 1. What is this one? This value is 2. The next one is 4. So one way to do this is to add up all of these numbers by conversion, but that's too many additions, right? So what you do is, instead of doing that, here's a nice trick. Think about this plus 1. What would this plus 1 equal to? 0b1. If you were to do this addition, what's going to happen? 1 plus 1 will give you a 0 with a carryover of 1, right? That's going to affect the next one. It's going to add up to another 0. All right, so what do you think is going to happen? What's the next number?
1, 0, 0.
1 and then, no, it's going to keep going, right? So 1 and how many zeros? No, no, you're not getting what I'm saying. You add a 1, then 1 plus 1 gives you 0, and then another 1, and then it keeps producing carry, right, to the next digit. And every time you add to the next digit, it creates a 0 and a carry until you move on to this last one, right? So it's going to create humongous number of zeros, right? But at the end of the day, it will just have nothing more to add to, so it's just going to produce a 1, right? So it'll be 1 and then what? 32 zeros, right? 1. Okay, that's 32 zeros. And therefore, this is going to be in decimals, it'll be 2 to the power of 32. In Python notation, this is power, 2 to 32. That's the highest number. Oh, but no. But this is 1 less than that number, right? So this will be 2 to the 32 minus 1. Now, if you didn't understand what I'm saying here, let's just think about in the decimal world. If you have 99999 plus 1, what do you get? You get 1 and then how many zeros? 5 zeros, right? Right? Because every time you add, you get a carryover. It's the same exact situation. If you were here, if you had this number and you had to think of going 1 more, what else can you do? Because this is the highest number you can represent using 32 digits of binary, the next number will have to use 33 digits of binary. And the smallest number that you can represent using 33 digits of binary is this number, which is equivalent to 2 to the power of 32. Is that good? Yeah. Is that right? No, just a minute. Keep confusing this. Right. 1, okay, if you have 1, that's 2 to the first power. No, 2 to the 0th power, right? If you have, I always have to think about this. If you have 0B100, that's 3 digits in binary, right? What is this as actual number? It's 2 to the, no, it's 4, right? 1, 2, 4. This is 4. This is 4. So this is equal to 4, which is 2 squared, right? Yeah. So make sure that you know the relationship between the length of the digit and what power this. It's 1 less, right? So if this is 33 digits, it must be 2 to the 32 power. Is that good? All right. All right, so now seeing that this is the highest you can represent is 2 to the 32 minus 1, let's see how large that can go. Using a calculator or something, you get this minus 1. This is the highest a 4-digit integer can represent. How many digits is this? Yeah, definitely can hold 8 digits and some more, right? Yeah. So you can even definitely store all 9 digits, and you can even store 10 digits as long as the first digit is not 4 or more. If it's 3 or less, then that's okay. So that's how you do this. Okay? So we just determined, on the other end, if you use 2 byte integer, what will be the maximum it can hold? 2 bytes is, instead of 32, how many bits? 16, right? So it'll be 2 to the 16 minus 1. It's going to be that. That's too low, right? So the 4 byte is the least you can use. So that's what we figured out. And after figuring this out, we can say 4 bytes per each employee. And then you multiply this to 2,000 employees, so 8,000 bytes is what you need. Is that okay? All right. All right, so let's move on. So this is something called a hex editor. How many of you use the hex editor? Anyone? No? Okay. Back in the days when PCs were not that powerful, you could hack. And also, nowadays all the games are online, right? you can't hack your own player stats because they're hosted on some server and they're protected by passwords, right? But in the old days, all the computer games were not online, but it was local. It was running on your own computer. So if you had a game that was hard to beat and it had to do with player stats like health points or some other strength or agility or some other things, dexterity and stuff like that, then you would actually go to the player data, but you would open the player data in a hex editor like this one, and you would try to figure out which code you have to change in order to max out your player stats. Okay. Actually, when my son was like 5 years old, so this is like about 10 years ago. When you're playing Minecraft, it was still local. So I installed on his tablet where he could play Minecraft in a hex editor like this one. Went into his inventory file and changed it to have everything diamond. Right? Diamond. Yeah. Diamond tools, everything. And then his friends came over and saw his friend became really impressed, and then later my son had to tell him that it was hacked, and he wanted to learn that as well. So there's also tablet version of hex editors you can use. Now, I thought about using this, but then you have to download this, install this on your computer. It's just too much. So let's do this instead. I am going to just use a custom-made hex editor in Python because you guys already have Python, right?
Yeah.
You have a computer? And can you open the computer and open this hex editor? This is a really crappy hex editor, but it just works. Okay. So let's try to do some activity with this. So type this in on your address bar.
Do you have a charger?
I don't. Let me ask you to do this as well. Install Notepad++. Do you have Notepad++? Yeah. You do? Yeah. So let me show you a nice website. If you go to Ninite, NINITE.com, you can choose all these free software, and I mean, the things that I definitely like to have on my computer are 7-Zip, FileZilla, Notepad++. These are the things that I like to put. And if you like to do music, Audacity is sometimes useful. Yeah, but if you want to install Audacity, you can do that as well. And you can also install Discord, Skype. You probably have these already, right? And sometimes I find it easier to have two browsers. So I would install Firefox from here as well. But anyways, if you do that, and then if you click Get Your Ninite, it gives you the bare bones installation file, so you don't have to click yes or anything. And it installs everything at once. So please use this to install Notepad as well. And if you're ready, tell me. Import to OS. And then do OS get CWD, which is the current working directory. So look where you're running this from. So a quick way to do this would be to just print it, print OS get CWD, and then whatever you get here, you can copy this and then paste it over here to see exactly where that formula that the Python is running from. Now, if you don't like this folder, then you can also also change directory with the OS, you can do os.chdir and then provide some new directory. Try to figure out how if you want to do it another way, but let's just stick with the thing that it has. Okay, so on here, what we are going to do is we're going to do right-click and new, and let's make a new text document. Okay, and we will just name the text document as hello. Hello.text. All right, so what do we do with it? We are going to right-click again. Now you could open with Notepad, but if you have Notepad++, I like this very much, so you can also open it with Notepad++. So open that. It's going to be blank. There won't be anything in there, right? How many of you have opened successfully so far? Done? Ready? Okay. Hello.text is that hello.txt. That was the name of the file. Got it done? Oh, I did right-click and open with. So right-click on the file and open with. And then I selected Notepad++.
Yeah, I'm trying to find Notepad.
Oh, you installed it and it doesn't show this? Maybe you have to turn your computer off and on. Okay, well, I guess Notepad is okay. Let's just open it in Notepad. Let's just open a Notepad, that's fine. And I want you to do something like space, and then this is a test, this is a test. You can change this text to anything. But try to put at least 2 spaces in the beginning, okay? And once you have this changed, so if you are able to do this in Notepad, same deal. You can do test. This is a test. This is a test. Okay. All right. So now what we are going to do is we are going to save this. So either with Notepad or Notepad++, save it.
Oh, I got it open in Notepad++. You have to like put choose file from computer, and then
That's how.
have to find where you downloaded it.
I see. You don't have right-click, open, edit with Notepad option?
No, you have to add it.
Oh,
So now that I
okay.
have added, now I can
Oh, I see.
do it.
All right. Okay, so now let's try to work with this file, hello.txt. Go back to Spider, and if you haven't, make sure that you copy this. Noah just came in here, so I just realized. You have to go to this 100 worksheets. Let me show you the link again. So, this website. Did you get it? Okay, good. So if you're on there, I don't want you to copy everything because this file, this part, execute something, I don't like it. So right before the if, copy this much. So right before if and above, copy everything. And then paste it in the console. Okay. Ready? Okay. All right, so we have this thing already executed, so let's see how this thing works. It's a hex edit. You provide the file name, and you can also have the start offset, and you can also change the length as well. But we'll just, these are optional parameters because you know how keyword equals the number, and if you have a default number, the program will, the function will execute without with these default values, so you don't have to provide them. So we will just use hex edit, parentheses, and file name. That's it. So we're going to do hex edit, parentheses, and file name that we just had was hello.txt. Okay. Hello.txt quote. Enter. Okay. So this is what we get. Is this okay? What did it say? Huh? Oh, okay. Hex edit hello.txt. Assuming that you put the hello.txt in the correct folder. Okay. Okay, how many of you got it done? So done? Whatever the getCWD gave you. So when you did the print to os.getCWD, you copy this, put it in the folder address, enter, and you're here now. Over here, you're going to do right click, new, and you want to have a text document and name it as hello. I already have hello, so I'll have to do hello. Once you have that, then you can open it in either Notepad or Notepad++. Text edit if you are in Mac.
Wait, but you did print parentheses os.cwd.
Get CWD. Yeah. Get CWD means get the current working directory. So did you do this print OS and did you copy this thing? It's also case sensitive, maybe. I know what it is. Okay. All right. So I mean, as a programmer, I am really sensitive about this extension. So I have everything as show extension. So for you, you'll have to do hello.text.text. So you might need hello.text.text, which is not the ideal. Did that work? Okay, all right. Okay, so some of you may have to do hello.text.text. Is that okay? Did you load it? Done? No, what's
Oh, you said you have to do I put text instead of txt.
yeah, txt. Oh, wait. Arrow. Enter. txt.txt. Oh, but you don't have anything put in there. You have to save it first. You have to save it. Okay, and then just press enter. Okay, just do it again. All right, good. Okay, so if you did this correctly, either hello.txt or hello.txt.txt, if you see this, you see that the very first thing is 20. What does that mean? Let's go back to our slides for the characters. So we were talking about ASCII characters, and in hexadecimals, hexadecimals 20 right here is what? Space, right? So because we made the first two parts as space, that's why you see 2020. Okay? And then capital T, what is that? Capital T is ASCII code 84, and in hexadecimals it's 54. That's why you see 2020 and then 54. Okay? Yeah. So if I want to go back and I want something like well, let's say you do this pound sign. That's 23, right? So what we can do is we can do 23 and then 23, right? And then I can just enter here. It says file edited successfully, which means if you run the same thing again, you now see that the first two hexadecimal values are changed to 23 and 23. Okay? Let's put enter. And then, now let's go back to my Notepad++. Now, if you're using Notepad, you will have to go back and click on that hello.txt. I don't know where that is. Yeah, so, oh, there it is. So you'll have to click this to open it on the Notepad. But if you're using Notepad++, and it's already open, when you click it, it'll say, this file has been modified in another program. Do you want to reload it? And you say yes. Now what do you see? Oh, I think this is a bug in my program. It shouldn't be doing this. Ah, I know. See, it's assuming that you have 64 length of the file, so there's some bug in this program. It adds this new thing. Okay. All right. Sorry about that. If you have a file length that's more than 64, that it's not going to do this, but it will repeat it to fill in this missing part. Okay. But anyways, you see that the first two parts are now changed to that, right? Okay. All right. So now let's do another one. Let's just. I'm going to save this again because I added a space here just to make it look nice. Right, so the next thing that you want to do is to go somewhere, and then you want to put the smiley face UTF-8 encoding. And the thing that I don't like is that if I do this, it shows you these other W3 Schools UTF-8 emojis, but the thing is, it doesn't show me the UTF-8 code. It shows me the Unicode hexadecimals, and I found that this doesn't work. So what you need is the Unicode is just another convention, another type of encoding, but in both Notepad and Notepad++, if you put something outside the standard ASCII code, it will read it as UTF-8 hexadecimals. And I found that this website, Compart, that one gives you, that's not true either. That's not what I need. Is it this? No, that's not it either. Oh, maybe it does. Okay, yeah. So this website, Unicode character, and it says the UTF-8 encoding is here. Okay. So what we are going to do is we're going to replace the very first digits as, 0x means the following numbers are hexadecimals. So ignore the 0x. What you want to do is F0, 9F, 98, 8A. So let's try to put that in there as well. Okay, so we're going to do hexedit again. I forgot what it was, so let me see. It's F0, 9F, 98, 8A. So F0, 98, I still forgot. Oh, 9F, 98. F0, 9F, 98. And then, what is it? 8A. You could use both. In Python, it's okay. In some other languages, probably not. In Python, you can use lowercase. But you could also use uppercase. It doesn't matter. Yeah. So now the file is edited successfully. Let's now go back. It says it's modified, reloaded. Now you see a big smiley face, right? Okay. And then we can have some more fun and try some other ones like, let's see. Same thing, smiley face, but devil face, UTF-8 encoding. Yeah, smiley face with horns, this one. Yeah, okay, this one. This one has, Oh, I think this is the one. Yeah, I think this is UTF-8. F0, 9F, 9888. F0. So let's do that again. F0, 98. Why can't I remember these things? 9F, 98. Oh, so it's very similar to the previous one, right? But that last digit, so the first three are equal, but instead of 8A, you have 88. So put 88, enter, and now you open it up, modified, now the one with the horns, okay? So you can kind of see how everything that's in your computer as a file is really digital. It's made of bytes, right? And you can modify it. This hex editor is a bit quirky. It's adding some other things, but anyways, you can modify it by changing this, right? So what about some other multimedia files? So let's talk about that. So we were talking about binary, ASCII code. And we had some questions about integers and binary. Okay, so here's a way that a picture is stored. So the most basic kind of file format for picture is called bitmap BMP. What other file formats for images do you know? JPEG, JPG, what else? The two most prevalent ones are JPG and PNG. Yeah. PNG is what's known as a lossless compression, and JPG is what's known as a lossy compression. So there will be another topic that we'll do next week. But what this does is it uses the RGB pixel value. So, every pixel has a color encoded as red, green, and blue with 1 byte each, 0 through 255. So the bitmap data would have RGB pixels. So every pixel will use 3 bytes. So for example, if you have a 100 by 100 image, you have 10,000 bytes, right? And 10,000 pixels. and that means you have how many bytes? 10,000 pixels. Every pixel is 3 bytes. So how many bytes? 3 times 10,000? 30,000 bytes. In kilobytes, what is it? 30 kilobytes. Yeah, yeah. Yeah, because 1,000 kilo. Yeah, kilo means 1,000, right? So
Yeah.
30,000 bytes is 30 kilobytes. Now, I explained the nuance between kilo with K, capital K only, and this other one with KI. But we're trying to look at the disk space. In that case, disk space are usually measured by just flat out 1,000, not the 1024 version. All right, and then it also has some additional headers. So there's like bitmap file header, which says this is an image file. If you're trying to open it up, try to open it as an image. And then there's a bitmap information about, sometimes it might have like location where the photo was taken, and it might have the camera it was used. If you modify with Photoshop, that information might be there as well. And sometimes it uses palette if it's palletized. So what it is that you want to save some space by not using all the colors. So if you're just using 255 colors, then the RGB values of those 255 different colors are stored. And if you do that, then every pixel will then be only one byte long, so the bitmap file will be shorter. Okay. But this is only if you're trying to use for some non-natural ones like clip art. That's when you're going to do this. Right? Okay, so this I already explained. Oh, in some file formats, such as PNG files, have transparency as the 4th byte for each pixel. So if you have say 50% transparency, it doesn't change anything about the picture, but when you overlay 2 pictures, then the one that comes later will have transparency in it. So for example, if you have a red letter on a blue background, and those are 2 separate files, and the blue is 100% not transparent, and the red is 50% transparent, and you overlay it, then you end up with the purple text. Okay, so that's how things work. Can we do just 5 more minutes? Because we kind of spent time making it. Yeah. I just want to finish this. Right? Okay, so okay. So in C++, there are short int, long int. Short int uses 16 bits. Oh, okay. Long int uses 4 bytes. Okay, I thought it was the opposite. Right? It was 8 and 4. Okay, so since the integer uses the leading bit for 0 for positive and 1 for negative, so here's something to think about. If you have 1 and 15 zeros in a short int, then what does that mean? It is 2 to the 15th power number. That's what it is. So it's in the ballpark of 32,000, 33,000, something like that. But that's if the integer is taken as just an unsigned integer. But if you think of it as a negative, the leading one could be thought as negative, then that number is going to be treated as -0. Because the leading one is treated as negative, and then you have a 0. Okay. So the short integer can represent numbers from -2 to the 15th power to 2 to the 15 minus 1. Oh, if it's this way, then I think that number would be negative 1. All right, now question, what is the highest number that can be represented by a 64 signed integer? What about unsigned 64 integer? So if you have a 64 signed integer, then you would use the very first bit for a sign. So 63 bits would be all the bits you can use, and that would give you the highest number as 2 to the 63rd power minus 1. This minus 1 is something that we talked about before. It's this minus 1 here. Right? Does that make sense? Because the very first digit is used for a sign. It's plus or minus. So that signed integers can represent negative integers. Yeah. But unsigned 64, it's 2 to 64 minus 1. Okay. Now, if you want to go higher, and that's definitely used for encryption and decryption algorithms. So, for example, RSA 2048 is one of the standard encryption methods that uses 2048-bit integer. What is that? That's like you divide that by 8. So that's a 256-byte integer. That's really big, right? And for those, you have to use an external library, something like big integer. And over here, you can use arbitrary size integers. In Python, integer can be any size, so there is no limit to the highest number it can represent. However, sometimes having uniformity in size is desired for speed and efficiency. In such a case, NumPy package allows int 8, int 16, int 32, and these as well. Okay. So I'm going to do a demonstration of NumPy next week. Just two more stuff, so we'll do that next time. So what do you do about decimals then? Well, decimals, you have 3 parts in the decimal. So if you have a 32-bit float point decimal value, then the leading term again is for the sign. 0 means it's positive, 1 means it's negative. And then 8 bits are used for exponents. So it goes between 2 to the, so 8 bits is 255 max, right? So whatever this number is, you subtract 127 so that the exponent can vary between 2 to the negative 127 to 2 to the positive 128. Okay, so those are the exponents that this could be. Okay. So when you have, say, what is 2 to the negative 1 power? It's 1/2, 1 over 2. Oh, so that's a decimal, isn't that right?
Yeah.
Yeah. So that's what's happening here. By using this value as a negative value, you can represent that as a decimal. Okay. And then the rest part is some value here. Okay? So you use these as the fraction part. So this is the significance value. So significance value can be used. So that's called 32-bit float. Now, I don't want to go too deep on this, so you don't have to know how this system works. Well, you just have to know that there's a single precision float. It's important. Single precision is 4 bytes. That's something that you have to remember because we do use it in machine learning. Okay, and then there's the double float, which is 8-byte float, and your graphic card. I noticed that some of you have a gaming laptop which has a GPU, and for playing games, your GPU is doing all the work, but because it doesn't have to be very accurate, it uses single precision. It's much faster using single precision. Now, when you try to use it for some of the machine learning algorithms, often they might require it to be double precision for scientific calculation stuff, and that's lot slower in your GPU. So there's some other GPUs like H100, which is like more than $10,000 per GPU. Those can do double precision efficiently. So that's the kind of thing that you have to remember. The actual implementation of how this works, you don't have to know, but of course, if you're interested, you can still know. Right? Okay, so that's